Steel weld microstructures. By the weld microstructure, what we're talking about is the metal that was liquid, then became solid, right? What type of microstructures would we see there? And what we want to discuss here is a document of people who got together and agreed what name to give to these microstructures you would see inside the weld nugget. By the way, it's not all that different than what you see outside the weld nugget too. There are some subtleties here and there. This document you will have in, it's already uploaded with your notes. I have a question here. I have a question about the Eureka formula, and let's see if I, Eureka formula. I don't have the notes in front of me, and I couldn't, but I believe it's very, very clear. So if at the end of the class that is not clear looking at your notes, then we can look in the 10 minutes we have. But I would need to look at the notes, which I believe are quite specific. If anybody can help with an answer for Natasha, you can put it in the chat. All right. So the microstructures, these are things that we have already discussed last week and things that will go in the exam today. Not the content of today, because I'm going to teach you names for these things, but things you're already familiar. So thank you very much, Ryan, for the answer. All right, so you already saw this image of the microstructure evolution in ferritic steels. And we said, and this is part of what you know for today's quiz, right? This is the austenitic grain. And as it starts to cool down, the first part that transforms depending on the cooling rate. But when you see a ring of a microstructure, this typically is the austenite in the primary ferrite in the grain boundary of the austenite, right? And then as the cooling progresses, we might see other microstructures like these little worms here that we call primary acicular ferrite, and these other lines here that are the product of a more of a harder transformation that is bainitic in nature, and we are going to call these ferrite with second phase aligned. But I didn't show you any photos. That's what we're going to do today. And in quiz 3, I'm going to ask you to recognize some of these microstructures. So the document we're going to be following is this IIW guide to the optical microscopy of the weld metal. And it's relatively old, and there have been some updates, but actually, I think the updates make things more difficult with less, makes things more difficult with little gain. So let's see what microstructures we discussed in the previous slide, and the microstructures we are going to, what they look in a photo. So here we go. Here we have the primary ferrite at the grain boundary, and they call it PFG, primary ferrite at the grain boundary. And you get to see it because it makes kind of loops. You see how this is marking kind of a boundary. It goes like this is the Widmanstatten ferrite. We're not going to worry about this right now. What we're going to worry is how this makes kind of a boundary. See how it keeps going here. And of course, it's not perfectly continuous. And it takes a turn here, or maybe it went continuously here. But you see how it makes kind of a loop. This we call PFG, primary ferrite at the grain boundary of the austenite. And we already discussed it. We didn't give this formal name PFG, but we did discuss the primary ferrite that is at the grain boundary of the austenite. Then there's other type of primary ferrite too. There are big chunks that are nucleated inside the austenite grain, right? They are not as common as those that are on the grain boundary. And when we have these big chunks, we call it PF, primary ferrite I, because intragranular, right? And here you have a photo. The one who took these photos is Alejandro, your TA, and they're excellent photos, and they're really very representative, right? And here you would see again how we have this loop of PFG and this big chunk inside that is the PFI, primary ferrite intragranular. Now, these two structures I discussed so far, the primary ferrite at the grain boundary or primary ferrite intragranular, they nucleate and they grow through a diffusional process. It's more or less what you would expect from the phase diagram. Now, I want to discuss a number of microstructures that now involve a process that is not just diffusional, but also, if you remember, is a hybrid of diffusion and displacer, right? A kind of a hybrid between what is the transformation into ferrite and carbides and martensite. When we look at the CCTs, which we look in much detail, and you're going to be looking at CCTs today in your quiz too, we could recognize the primary ferrite, we could recognize the perlite, we could recognize the martensite, and then a whole bunch of, there is another thing that we call bainite, right? The CCTs always say bainite. And I mentioned to you that bainite is a generic name to something with this hybrid characteristic of this diffusional and displacer. But there are many different types of this type of unhappy transformation, right? In which like it was too fast to transform diffusionally, but still not quite martensite. One of these hybrid mechanisms, one of these bainitic type of mechanisms is this acicular ferrite. And acicular ferrite is a very convenient microstructure. And actually, we're going to see lots of acicular ferrite in welded metal, and not so much in the base metal. And the reason we see acicular ferrite in the base metal is because we intentionally nucleate it, typically with titanium oxide. And that's why filler wire has some amount of titanium that base metal seldom has, and also why we don't want to have zero oxygen in our weld, because we need some amount of oxygen to oxidize that titanium. And when we nucleate the acicular ferrite, it looks like this. You see that it's kind of a basket weave type of microstructure. And this is a very tough microstructure. It's a very desirable microstructure. We are in the fall and we haven't had our first snow yet. But after the winter comes and spring comes, sometimes we get to see how the puddles froze with all these dendrites of ice. And then when they start to thaw, the dendrites are still there. And I have seen it. I didn't make a video at the time, but I wish I did. Sometimes when you get these interwoven dendrites in the thawing puddles, you can pick up the ice, and the ice bends because all these dendrites are like making like a basket weave and giving it a lot of flexibility that ice in itself doesn't have. It's quite amazing. That's exactly the same idea we have in acicular ferrite. So that's a very desirable microstructure to have. Other microstructures that also of a mix of diffusional and displacive transformation nature, right? That fall under this bainite part on a CCT. We call ferrite with second phase, obviously. ferrite and some sort of carbides, right? Exactly what we would expect. And there are a number of subtleties about FS. An important one is called FSA, and it means ferrite with second faces aligned. And you get to see them here where we are pointing with the arrow. You get to see a very clear texture about how we have the ferrite that we call laths, the laths of ferrite, and in between we have this darker thing that is this second phase. We don't need to worry about what that is, but if it is an iron carbon diagram, is cementite, right? Now, this microstructure, I am going to ask you a question. Do you think this is going to be tougher than a secular ferrite or less tough than a secular ferrite? Just by the look it has. What I would like to hear some speculation, what to expect about the mechanical properties of this microstructure. It's less tough, of course, it's less tough, and you can see the crack patterns that can develop here, right? Well, a secular ferrite is a basket weave, and it's very tough because whatever you do is kind of all interwoven. This one is like a zipper that can unzip, right? So we see two bayonitic type of microstructures, one that has lots of toughness, one that doesn't. And when we look at them in the microscope, it matters to see, oh, what do I see more? More of this basket weave as secular ferrite, and I can anticipate a tough material. Or would I see a material with lots of this second phase aligned, which would be less tough? Then we have this other one that is FSNA, that is ferrite with second phase non-aligned. And we get to see this quite a bit less typically, but it's here. And the characteristic of FSNA is that in this case, instead of being clear lines, instead of having the second faces clearly aligned, these second faces, these dark spots, they look kind of random. Of course, this is metallurgy and not mathematics. I already showed you in our first slide how metallurgy is so difficult to pin down and how it's inexact, and our instruments are not exact. So if you ask me at what level you consider something to be elongated and at what level you can say you would consider something aligned or non-aligned, I don't have a straight answer for that. It's the type of answer that people would say, I would know it when I see it, but not everybody would agree all the time with things. So with this understanding that reading these microstructures involves a significant amount of subjectivity, right? We get to see something that can be very well aligned or something that is kind of spots. And those would be FSNA. In this other image, we have ferrite with carbide aggregates. So in this case, the ferrite with carbide aggregates is talking about fine mixtures of ferrite and carbide aggregates. If we know it's perlite, because either we did some deep characterization or because we know from the phase diagram that is what to be expected, then we put FC, ferrite with carbides, P indicating is perlite. This is what we see here. This is another image Alejandro took, and Alejandro gives me this interpretation with which I completely agree. We're gonna see that later, that all this white, you already know this is primary ferrite. This smaller white is also primary ferrite. We'll discuss that. The black in between, that's perlite, and we know what it is. And we would mark this black here, similar to what it says here. We're going to mark it as FCP in this case. And then we have martensite, which we didn't put it here, but is marked with an M. And martensite, as you realize, has a very different look than the other ones. Look, this or this other one, they have this clear black and white contrast between the ferrite and the carbide. But in martensite, all of a sudden it looks like frosted, right? And we don't see these clear grains, right? And actually, if you look at it in higher detail, you would see that all these faces here, they have a clear texture as if they were made out of wood, right? So this is the martensite with which we are very familiar from our CCT work, which we'll be discussing this afternoon, after the class. Okay, so I also included the document, and this set of slides has kind of a little guideline to recognize these images. So martensite you recognize from the CCT, primary ferrite you recognize from the CCT, and perlite you recognize from the CCT, and FS, whether it's FSNA, FSA, or acicular ferrite, all these three, none of them is called bainite, but that's where they belong in the CCT diagram. They belong in the bainite region. Okay, so this is much in line with what we have been discussing regarding the microstructures of carbon steels. Okay, what I'm going to do now, what I would like to is to discuss now the heat affected zone. So let's, I'm gonna switch the slides. If there is any question, you can bring it up as I switch slides.